All right, so thanks everyone for joining us. My name is Nacho. So I work at Thot and we're a spin-off from EPFL. And our main target is sort of building the next technology for data management and analysis. So we'll briefly go over open science, then I'll give a story to kind of highlight in detail the issues I think are more pertinent these days in terms of data management. Then I kind of want to briefly go and talk about where we are right now in terms of what technology we're using and where we can go. So in this modern day, the researcher spends a significant amount of time in data and analysis. And for this to work well, I guess as a collective, there's, for this to work well as a collective, there's two main components that need to work well: this openness aspect and reusable. So when we say open, we mean accessible. So for instance, if the data that the researcher published is behind a paywall, it's difficult to access. It also needs to be findable. So for instance, it could not be behind a paywall, but perhaps the only way to get that data is to send an email to the professor or a researcher. And lastly, there is this question of transparency. And in some way, this is an umbrella word, since if it's neither accessible or findable, in some sense, the data is not transparent. Further, it could also maybe mean that the researcher did not include all the data. And I think when we say transparent, it also needs to be intelligible. And then this will basically be, I think, a good segue for this next component of reusability. So even though it may be accessible and findable, if it's not clear how the data is structured, then it's in some sense not really transparent. And the structure is important. Why? So imagine we want to reuse certain experiment or even an analysis. If it's completely unstructured, it'll take a significant amount of time to actually be able to use it. So effectively, it's not really transparent. And another, I think, very important nuance is this notion of modularity, which is perhaps talked a bit less. And I think this is really a more modern notion within open science. And so maybe to give an example here, it's really the question of, is your data and your analysis mixed together, or is it separate? Is it modular? And why this is important? So let's imagine as a researcher, you have your data, and in the same script, you also have your analysis. If the analysis is somehow proprietary, it's going to be difficult to share it. And also, conversely, in a way, it could be that the data is basically want to be kept private, but you might want to share the analysis. And so if in the same Excel file you have both, this is really an issue in terms of reusability. And perhaps the final question I want to, or point I want to raise here is kind of who are the stakeholders? So when we talk about open, of course, the main one is the scientist. So we as a collective, or for the scientist, it's important that it be open. But I think we sometimes forget, and it's important to highlight that everyone else in some sense is part of the discussion. And I think this was highlighted. So I think 2-3 years ago with COVID, there was a big backlash against the scientific community about skepticism. And so, of course, if we're not transparent enough, this gives ammunition to all these science deniers. And I think it's important to keep in mind that, this is not only for ourselves to work better, for scientists to be more effective, but also as a society to build more trust in the process. And in terms of reusability, again, main stakeholder is a scientist, but more and more, it's important to consider machines. And by machines these days, that effectively means machine learning models. If data is structured and modular, it's much easier to build models for it, to feed that data in and to create the latest, and I guess, AI models. And so this is a rough overview, I think, of a more modern take in this question of open science. So now I'd like to tell a story about a friend of mine, Alice, to maybe see a more detailed example of all these points. And so Alice was a PhD student 2 years ago, and she was in her final year. And she was really excited because finally she could be presenting at a conference. she was working on this latest idea she had. So roughly, she wanted to see the effect of certain proteins on certain cells. And so she would go early in the morning. And so it was this a classical manual procedure of pipetting these different proteins and one by one inserting them in different Petri dishes. And so towards the end of the evening, she would be able to collect some of the results. And so here already we start seeing this kind of pernicious effect that occurs within science. We work hard, then you are tired. And so, of course, it's much easier to quickly see and get an idea of what's going on by running an analysis within the same Excel sheet where your data is living. And at an individual instance, it kind of doesn't matter because very quickly she gets an idea of the mean effect of the protein. But of course, as time goes on, she has some new ideas she wants to test. And then this data and sort of bad habits start to accumulate. But at this time, it wasn't a problem. I remember talking with her, she was elated because she was getting some really interesting results that she could compare. And so time was drawing near, and I think she had about still, I think it was 1-2 weeks to prepare, I guess now, to put all these contents together into a paper that she can then present to the conference. But at this time that while talking with her professor, they realized that they kind of had missed an important document in the literature, which would be important to highlight. In essence, that meant adding the results of this other research group into her current studies, incorporating the data and updating analysis. And so suddenly she was a bit stressed because time was drawing near, and this was quite important because you don't want to go to a big conference and be missing an important part of the conversation. And so she emails the professor, and very quickly he answers, and he says, of course, here's the data, here's the analysis. And this is this very typical case that will happen, that essentially the colleague will zip all the files into this folder, which you can then get. So the issue, and this goes even back to what Alice was doing, is that in general, oftentimes there is this notion of a data dump. So if you're lucky, all the files will be well organized, but very often you will be in the middle of this unstructured mess. And so within this deadline framework, I remember her stressing out a lot because she had to figure out which is the important data. Even when she realized which files were kind of important for her, she had to disentangle. She had to figure out, okay, which part is the actual data that they took and which part is the analysis, the secondary experiments, because she wants to run her own analysis. And maybe she wants to take those analyses for her own experiments. This is a huge manual labor. And when you're under stress, it's not a nice task. And I guess happy Valentine, everyone. There's a heart here on the back for those watching the slides. So this was not a nice process for her. And I think it got even worse when she realized she also needed to add the important comments about the lab notes that we're taking. Under what conditions were the Petri dishes preserved and all these things. So she had to, again, correspond with her colleague, get another email, and she has to like manually figure out, okay, these notes match to what Excel data file. And so after a long work, she finally submits her document, and then it gets accepted to the conference, and then she goes to give a talk. And so I think I kind of want to, before finishing up on how she performed at the end of this conference, ask this question, what if, like looking back and especially remembering her stress, was it really necessary? Is there not maybe a better way to go around it? And so this part is a bit of a thought experiment in seeing how, if we change certain things, if we perhaps try to be a bit creative, this process could have been much easier. And so looking back, the first one was really about being structured. So when she unzips the folder, she has this huge Excel dump. What if this was structured? What if, in some ideal sense, every experiment or data is structured the same? In the sense that at the bottommost, that is in the beginning, you start off with this raw data, really the measurements that you take from the experiments, in this case, from the Petri dishes. Then even results are data, right? Because these are either point statistics like the mean, or it could even be several values, which at the end, in terms of hierarchy, should come above, right? Why? Because we compute them from the first layer, that is from the actual data. And you can then recurse because you can start doing meta-analysis and comparing results of results. So in some ideal sense, data will have this inherently tree structure to kind of support it. And if it were always organized like this, it would be easy, right? Because if you're Alice, you look at the tree and you're like, okay, I want to run my own analysis, so I just look at the bottom of the tree. If I want to see their analysis, I have to look at upper layers. And then I think what's also cool is that if you have this kind of framework, it sort of becomes trivial to extend it. So if you go from 2 different variants of proteins that you're testing to a third one, it just means you are adding a new node to your tree. And so how does modularity come into play? So we talked about this, in this high setting of like separating data and analysis, but I think it's important to say concretely why this is actually such an important nuance. So really hammering it again, it's this question of separation of analysis and data. And so if it were separated, then when we are actually performing analysis, so going back to the structure, at the lowest level, we have this raw data. And somehow the analysis is the glue between results, which are again also data, and the original source of samples. And so what would happen is you start with the measurements you took from the Petri dishes, you get mean statistic p-values, and for those statistics, then you also run an analysis to get an overview comparing these 2 results. And so if you're Alice, if it were possible to, have gotten this from the beginning, then it would be easy, because then basically if she wants to run her own analysis, she discards every file above the lowest level. And instead of these red analysis, she puts her own blue analysis, runs it, and gets her own results. And if she wants to run the same analysis that her colleagues were using, or this other professor, she replaces the bottommost files with her own data and preserves these red analysis, and then getting the corresponding results. So it becomes really kind of like playing with Legos. You're just switching them around, and it just makes the whole affair much, much easier. And maybe to reiterate and be more concrete, what we're really saying is from these root files, we give them as an input to the analysis, and then as an output, we get this new data. And the last comment, and it's this idea of an integrated nodes. And I want to spend some time here because I think at first it seems simple. So what do we mean integrated nodes? So I remember when talking with Alice, it was really a huge time drain for her asking about these lab notebooks. So typically these days, what scientists use are known as ELNs, so electric lab notebooks. And these are dedicated solutions where you input how much time you took for certain experiments, what you did, under what conditions did you do them. And because these are separated from your workflow, because these are separated from the data, it really means that you manually have to look at what happened. And for Alice, you have to imagine like whoever wrote those notebooks, this was months ago. So even if she could have a back and forth with this person, he would also struggle to understand which nodes correspond to which data or analysis. And so in this ideal situation, these nodes would be integrated to whatever tool you're using. So when Alice is looking at this project, she can just click at the different parts. She can just click at the data and quickly see, okay, these results were taken on a Tuesday evening, 18 degrees Fahrenheit, etc. So very quickly, very easily, she can understand what was going on. And similar for analysis. And again, it's a huge leap of going from two separated pieces of technology having to manually match versus really with just one click having it be part of the system. And this last point is kind of this open question. So the thing we presented is really nice, but for that to be actually open, we would need something like a repository. And so let's imagine this ideal structure that we looked at before. So you really have this organized tree, which has the data, which has the scripts, both modular, and it has this notebooks. So then at that time, Alice could have perhaps just looked into this repository and checked, oh, who has done these kind of experiments, rather than only that professor. And then imagine even it was only the professor who had that there, then she just downloads this repository. And here it's very important to understand what we mean by the repository. So repository is a collection of these projects. And the project would be this all-encompassing object, which contains structure, modularity, and lab notes. So she would instantly be viewing whatever the researcher was viewing. And if for some reason it's a tool she already used before, in a matter of minutes, she would quickly understand what is going on. And it would be kind of trivial to really change analysis, add data. And especially looking back at the amount of stress which she incurred because of having to go back and forth, having to manually check stuff, it would really be a game changer. And so perhaps if we go back and look at everything we went through, is really the ideal thing we described really satisfies all these requirements. And I think what's important is that what kind of made it possible was focusing on the reusability. I think a lot of emphasis has been put on the open part. Let's create these open repositories. Let's have open lab notes. But if they're not really reusable, if they're not practical per se, then in effect, they're not a useful solution. And indeed, if we ask the question, how close are we? Where are we right now? In some sense, yes, everything is possible in terms of what the open science asks for. We have these open repositories. There are lab notebooks. There are analysis programs like Excel. Everyone can share them. But the fact of the matter is, the reality that we are currently in is that each of these solutions have drawbacks. The first is simply from the fact that these are separate solutions. And this goes back at this analysis program. So your Excel file, perhaps even your data, and the lab notebooks, they're disjoint. And the mere fact that they're disjoint means that it requires effort to check between both. Why does it need to be this way? Even for the data repository, it requires additional steps. And everybody has a different way of organizing their data. So even though there is a single source of truth, even though it's open, in effect, it's not transparent because everybody has to figure out how everybody's working. And so at Thot, this is kind of the issue we want to address. Build a tool that's simple, based on this thought experiment of how it would work ideally, where we integrate these main components in such a way that what we talked about before, this tree-like structure, modularity, having the scripts in a separate place, being able to share not at the data level, not at the analysis level, but at the project level, is what we believe can bring us closer to open science. And so I think this concludes this first part. And in the next section, Brian will look at more in detail what it is we have built from a bit of an abstract setting.
So Nacho just gave us a great overview of theoretically what we would like a program to facilitate our research data management to look like. Openness, modularity, reusability. But what does this look like when we actually implement it? And this is where Thot comes in. This is a software I developed during my research. And so it was really built by programmers or by researchers for researchers. And we're just going to take a little toy example of, imagine you just got hired by a fireworks company. And at this fireworks company, they want us to test some new recipes that they developed to see which one is quieter. We're trying to protect everybody's ears. So the test they want us to run, they created 2 recipes, A and B. For each of those recipes, they created 2 different batches, and they already did all the measurements and wrote the analysis script. So all we have to do is build up this project and give them the results. So we can start with our project at the top level. We'll then add both of our recipes, mimicking the project structure, and then we can add our batches. So you can see here, when we build our project tree, we're just mimicking our experimental structure in our research project. We can then add our data at the bottom level. And then they give us our analysis, which we can assign. We're going to assign the green analysis to run at the bottom level, the blue analysis to take those results and derive the results for each recipe. And then finally, we'll have the red result at the very top to give us our comparison between recipe A and recipe B. So what this looks like is, first, the green analysis is going to run. It's going to pull in our raw data and produce some summary results. Once that's complete, our blue analysis is going to run. It can reach down into the subtree, pull up any data, and create a new summary result for each recipe. And then finally, once both those are done, our red analysis can run and give us our final results, which is maybe in the form of a table comparing recipe A to recipe B. And what do we find? Well, we find that recipe A is very quiet and recipe B is much too loud. We give these results to our boss and they say, this is really nice, but I want a good way to visualize this. I want to see it in a bar chart to really get a sense of what the noise difference is. If we were using Excel, we'd have to go through, recollect all the data, add this bar chart. But what we can do with this modular system is just take another analysis, purple analysis, that takes the results in and produces a bar chart. All we do then is just rerun our project. All the new results are incorporated into this bar chart, and it pops out without essentially any additional overhead. Now, one of the scientists comes up with a brand new idea for a recipe. They call it recipe C. They go run the experiments, 2 batches again. Because we've already built up our analysis and project tree, it's easy for us to incorporate these results. We just add this additional tree into our project, add our raw data, assign the same analysis that we want to run, and then using this program, the process of incorporating the new data is automated. So you just push a button, everything's incorporated, and all the new results are there. We have both the table and the bar chart. So we've really developed this program to be as easy as possible. You build the project structure to mimic your experiment structure. You add your raw data in, you assign the analysis that you want to run, and then you just click a button and the program automatically pulls in the results, producing the new results all the way up the project tree. And the nice thing is with the modular data and analysis is you can add either at any time, rerun the project, and the results are automatically incorporated. So now we hope that it's your turn to play around with this. We have a website if you want to check out the prototype. We'll be launching the production version soon. And give it a try, see if it works for your research. And hopefully you can join our community to make science a more open place. And if anybody has any questions or comments, please just raise your hand and we can have a little bit of a discussion. And I saw there was a thing on chat.
I think it was just loading.
Oh, okay. And If anybody has any
Also,
questions, comments, or
please,
anything,
Paul.
you
Yeah.
can just.
Yeah. Hi guys, thanks for the talk. I'm just wondering, you were talking about the analysis scripts, and are these limited to any program, or can you basically integrate any kind of script to the analysis part?
Yeah, so the scripts come in 3 different levels. The first level is you can program your own scripts. Right now, we only have Python bindings, but we'll be creating R, MATLAB, C, C++, and all these additional bindings. You can see here the API, it's very simple. There's only 5 API calls. And you can kind of think of the Thot as a framework that goes around your analysis, essentially acting as a database. So that would be the bottom level. The level above that would be a templating language, which is essentially a spreadsheet where you can template what your analysis looks like. So this is, if you're familiar with no code or low code, it would be this sort of solution where you can just visually say, this is where my data is, this is what it looks like, this is what I want to do to it. And then the top level is, as Nacho mentioned, these online repositories allow you to share both your data and your analysis. So if somebody in your field has created a customized analysis that you want to use, if they make that public, you can just go in, take that analysis from their project and include it in your own project.
Right, I see. Yeah, that's awesome. But do you guys give any hints on how to actually structure the raw data? Because I mean, if I have a script that just fits my data, right, anybody else would still need to implement my data structure.
Yeah, so in the scripts, you can have parameters that allow the user of your script to customize certain pieces of it. So all this automation is enabled through metadata tagging. So maybe you tag your data with a certain name, maybe you call it like type A, but the other person wants to call it, you know, level 1. You can use the parameters to allow them to customize which metadata they're actually looking for and still use the same analysis script.
All right, I see. I think that's a great thing that you're doing there, guys. So thanks very much for talking about it.
Awesome. Thanks so much, Paul. Really appreciate it.
And I saw in the comments, someone was asking if this will be available for R. And so I think the cool thing is that we built this with the Rust. And so it's extremely easy to add several bindings. Right now, we just have Python, but I think it just takes a couple of days to, or even less, to add for C, R, and many other languages.
Yeah, so for the R bindings, I would expect those to be coming out in March.
And so if people want to get in touch, what is the best way? Oh. Yeah,
so if you go to the website, you can download the prototype there, get it working. You can also join our Slack channel. If you run into any issues, we're still a fairly small community and we're reaching out to individual researchers. So if you want to get started, even if you don't have any programming experience, hop on the Slack channel, let us know, and we can even help program your analysis with you, taking your current workflow of copying and pasting between Excel sheets and moving it to this automated system where you can just click a button and then it works. Cool. If there are no other comments, I think we'll sign off here. And hopefully we get to meet you all in person one day and help you with the program. And if not, have a great rest of the I Love Data Week. And hopefully we can all make a push towards more open science.
And happy Valentine's, everyone.